Welcome, everybody. Welcome to those who are joining us virtually. So this is our final session in the stream. So Paul Barrett will be showing us how to use Julia in astronomy. So Paul, over to you.
Okay, thank you. Welcome to the Julia in Astronomy BoF. I'm Paul Barrett. I'm a research professor at the George Washington University, as the title slide shows. Let's see. So the brief outline is, what is Julia, for those who don't know what the language is. And then I'll go into why Julia, why should we use Julia and think about it. And then in terms of kind of discussion, the next issue is AstroJulia. There's actually a website, GitHub site called AstroJulia. I'll show you what software is available currently. And then the next hour is more open discussion in terms of what next for Julia. For those who are interested in Julia or might be interested in Julia, what type of software, would you be interested or you think is a priority? So feel free to interrupt at any time. Pretty informal. So what is Julia? Julia is a scientific programming language developed by, in 2009 by Jeff Bezanison, Stefan Karpinski, Viral Shaw, and Alan Edelman at MIT. The story is that two of them, I forget which two, were going to go out to dinner, and for some reason they didn't actually have dinner, but they sat in the car, and one guy said, I really like to develop a good scientific programming language. And so that's how it began. It was officially unveiled in 2012, and version 1.0 was released 3 years ago in August 2018. Development is fairly rapid. The current version is 1.6.2, and 1.7.0 should be released in the next week or two. So why the name of Julia? Well, they just thought it was a good name for a programming language. So there's nothing big behind that, the name. No interesting story. So why create a new language? If you go off to the julialang.org site, it says, the author goes, we want a language that's open source with a liberal license. We want the speed of C with the dynamism of Ruby. We want a language that's homoiconic with true macros like Lisp, but with obvious, familiar mathematical notation like MATLAB. We want something as usable for general programming as Python, as easy for statistics as R, as natural for string processing as Perl, and as powerful for linear algebra as MATLAB. As good at gluing programs together as the shell, something that is dirt simple to learn, yet keeps the most serious hackers happy. We want it to be interactive. We want it compiled. And with version 1, they've pretty much achieved all of those objectives. So for historical background, I don't know if you read the abstract, but 25 years ago, Joe Harrington and I proposed that the astronomical community use Python as its primary language for scientific computing. And back then, even when we were developing NumPy and PyFit or PyFits, and eventually Matplotlib, but particularly NumPy, we knew that there were issues with Python. But Python was a simple language, and it allowed you to add in C code very easily. Plus, it allowed Fortran style array syntax. So basically what I'm saying is, we knew back 25 years ago that SciPy was a two-language problem, okay? It required two languages, Python and C and C++. What Julia does is it solves that problem. It solves the two-language problem. The two-language problem is typically 90% of your app is developed in a slow language like Python, but a dynamic language, and 10% is developed in a fast static language like C or C++, which is NumPy and SciPy. So that's that. So we knew that. And so over the last 25 years, personally, I've been waiting for a language to come along to actually solve that two-language problem and for scientific computing. And I think Julia is that language. So as Virial Shaw says, one of the founders, we set out to solve the two-language problem back in 2009. Much of our progress in parallel computing was thwarted by the fact that while the users are programming in a high-level language such as R and Python, the performance-critical parts have to be written in C and C++ for performance. This is hugely inefficient because it introduces human error and wasted effort, slows time to market, and allows competitors to leapfrog ahead. This two-language problem hinders not just researchers, but also quant scientists, data scientists, and engineers in the industry. Quants are people who work in the financial industry, if you didn't know. And there's another aspect to the two-language problem is once you've written your code in C++, then the language is static. That code is pretty static, and to provide any additional performance requires rewriting that code. The one aspect of Julia is because the language and the compiler, the just-in-time compiler, is always changing. When you get a newer version of Julia, your code can actually run faster because it's recompiled with the latest optimizations. And this can make quite a big performance improvements. You can get changes of factors of 1, 2, and up to 10 times improvement just by subtle little changes in the code, in the optimization. So the two-language problem is critical, and that's the reason for Julia. So other aspects of Julia, it's high performance. Many tests show it's as fast, in many cases faster than C and C++. And there are reasons for that because of various optimizations that can be done. I'll give you one example. If you're adding a unitary array to some other type of array, the unitary array doesn't actually have to be array. It can actually just be a value of 1. It can be a virtual unitary array. And this basically eliminates that array. That's the size of that array, that memory, but it also makes the compilation or the computation much faster. So that's one of kind of the optimizations that can be done with Julia, which you're not going to get with SciPy. The other thing is parallel computations are easy. This is one of the features I really like about Julia. There are what they call macros. Julia has these things called macros, which modify the code or sections of the code. You can use what they call @SIMD, which is single instruction, multiple data, which will vectorize sections of code. You can use @threads, which will basically take a for loop, is the example there, and it'll run each iteration of that for loop in a separate thread. So if each iteration of the for loop can be parallelized, you can just parallelize it right there with a simple @threads. You don't have to know anything about parallelization or multi-threading. It just does it for you. I've gotten factors of, I have a 16 thread machine on my desktop, and I get a factor of 16 improvement, just like that, very quickly. The other aspect is that you can actually write GPU kernels and expressions in Julia, which will compile the GPU code. So you can get benefits of GPU compilation or using the GPU processors to do parallel computation. Another key to Julia is that it's composable. And what they mean by that is 2 separately developed packages will work well together. The example I give here is there is a data type called measurement, and that measurement is 24 plus or minus 4. Well, you can multiply that times the unit data type, which is kilometers per second, Okay, and now you've got a measurement of 24 plus or minus 4 kilometers per second. If I multiply that times a unit of 10 seconds, then I get 240 plus or minus 40 kilometers per second. I mean, that's Julia code right then and there. It will do, and so, you know, it will do the error analysis for you. It keeps track of all the units, and it's just like what you would write down in a paper. Python doesn't really provide these capabilities that I'm aware of. At this stage, I haven't used SciPy in a number of years. So I'm not sure that that's been added in yet. But this was one of the design features of Julia. The other aspect is Julia is a technical language. They designed it so that it understands Unicode and LaTeX. So you can use Greek symbols or any other type of symbol that you want in your expressions. So if you pull an expression out of a text, you can basically write it just as you see in the text. And so that makes for really simple, elegant code, and you know, very understandable. And for most people, the big aspect is, well, you want me to change a language, you want me to go from SciPy to Julia. You know, I basically have to rewrite my code. Well, not completely, because Julia was designed to work well with other languages, particularly Python, C and C++, and Fortran. So an example here is I can import NumPy as MP, and then I can start using the NumPy library to do mathematics. Excuse me, I'm going to shut the door. There we go. So I use the Python interface all the time to access radio astronomy data, and it's very quick. It's almost basically transparent. It's just like writing, you know, Python code, SciPy code. The other feature of Julia is it's a multi-dispatch language, and what they mean by that is the function that is run or called is chosen based on all of its arguments, all of its function arguments. Python is single dispatch. It only chooses that function based on the first argument. And this makes it difficult in Python to add new data types, particularly with operators. Like, I want to add type A to type B, but what if, you know, what if the expression's actually B plus A? Since you're only picking on the first type, it's very difficult. You don't really want to go and change the type B to know about type A. You know, if you're writing type A, you know about B. Multiple dispatch gets around this issue, and therefore it's actually much more efficient. The other aspect is you can write multiple different versions of a function based on the data type. So you can have a double precision floating version, double precision version. You can have a single precision version. You can have an integer version, and it will pick the right one for you, which obviously is a good optimization feature. The language provides optional typing, so you can add you can declare your variables as specific types, and that will improve performance and safety. And what else? Other feature I like is it has a very nice package manager, actually built into the command line interface. And so, for example, here I show I've gone into the package manager, PKG, and I can add the units package. It will download it and compile it, and within a few seconds, or maybe less than a minute, that units package is now available. And this feature is really nice because it kind of solves the version control issue, because your code is all Julia pretty much. Whenever you update Julia or something else, you can update your code and compile it on the fly for that version. Okay, so you don't have to worry about loading some package and find out that it's 4 versions old and it's not compatible anymore. And that can be a big issue. And I've had that issue with Python for a while. And finally, it's a general purpose language. You can do string manipulation. You can do OS calls. I mean, it's just like Python. You can do all of that stuff. You can do scripting in it if you want. So everything is, has pretty much everything you want. So here's a question here. Does Julia's support for units offer more functionality than AstroPi's units package? I haven't used AstroPi's units package in a long time, so I really can't answer that question. But my guess is that, yes, it's pretty fully functional. It will do conversion changes for you, unit changes. And because a lot of that, all the unit stuff is actually done symbolically, okay? Ask Julia. Julia is very good at symbolic manipulation. In fact, its symbolics package is 100 times faster than SymPy. So that's an introduction to Julia. If there are any questions you'd like me to answer or elaborate on, feel free to speak up. Do
you have any questions from the audience? You can also ask.
Okay. What do you mean by how mature is Julia's scientific package system? Can you give an example? I mean, you can do all the mathematics, pretty much anything you can do in SciPy, or almost everything you can do in SciPy, you can do in Julia, and you can probably do it better and it's more optimized. The one thing is Python only has like 3 array types, and Julia has like a dozen different array types. So they have sparse arrays, Hermitian arrays, and all of those interact with each other. Python doesn't have that concept really. So if you want to use sparse arrays, you have to stick with sparse arrays, but you can't mix and match sparse arrays and dense arrays. Where Julia, you can. There's FFTs. There's a huge effort for machine learning in Julia right now and auto differentiation. Things are progressing pretty quickly in that respect. Does that answer your question?
Yeah, Michelle, do you want to perhaps? Yes.
Michelle Lochner has a question. Yes, I know that the big issue, and I've had lots of responses about this, that we're so deeply embedded with Python now, or SciPy, that it's, moving to Julia will be difficult. And this has been the case. This was the case 25 years ago when, we proposed Python to the community. It's just, it's a recurring issue. I think one just has to, if you're writing new code, and particularly array type code, you might want to think about including that piece of code, writing it in Julia and see how it works out. The other aspect is that, if you've got code which is taking a half an hour to run in SciPy, you might really want to consider rewriting that in Julia, because you could probably get factors of 2 or 3 improvement in terms of speed. And that can make your analysis a lot easier. I know I've personally experienced that, where having writing it in Julia, my code runs a lot faster. So what other do we have?
So I think Jonathan also asked here that there's a lot of overlap between Julia and Numba. What's your thoughts on that? Numba is also, for those who haven't seen it, is a just-in-time compiled subset of Python. Speed-wise, it also gets comparable speeds to C or C++. Your thoughts here? On your side, Paul?
Yeah, I'm not that familiar with Numba. I mean, I'm aware of it. I don't know, the actual internals and how it works. But I think the limitation with Numba is actually the limitation of Python. And it really has to do with this whole issue of single dispatch and multi-dispatch. Python is still limited to single dispatch. So, if you go back to the arrays, you're still limited to the three different array types that Python has, whereas, Julia has a lot larger number of, array types that you can use. And there's also the issue of, composability, being able to mix and match these array types easily. So yeah, for a single array type, I'm sure it's highly competitive with Julia. But if you're working in much, more disparate type of analysis environment, and you need the different array types, then Julia probably will win out.
I think there's quite a few comments here as well. So Simon says that Numba supports dispatching a JIT implementation on variable types and some variable types. But yeah, it's not built into the language, and I think that's one of the primary points here. So yeah, so the integration is tighter, as he said as well.
Yeah.
Then Michelle has commented here, Numba is a bit restrictive at times. It's appealing to not need some of the tricks needed to make Numba work, so multiple return types, etc. Yeah.
I'm sorry, what was that one?
So there's so she just commented that you don't need all the tricks to make Numba work within Julia. So yeah, multiple return types and so forth. Okay, there's also
well, the question is down here at the bottom from Michelle, Julia and Python. Are we at the stage yet where we can run Julia and Python kernels in Jupyter notebooks? Well, do you mean that does Jupyter support Julia? Whether you can run them together? Gee, I don't know. I can't answer that question. You just have to try it. I'm guessing, I'm guessing Jupyter, will allow that. Since it's designed for both, Jupyter is designed for, Julia, Python, and R. So yeah, I would hope it'd be able to understand all three of them.
It's an interesting question because I know Colab, for instance, from Google, allows you to run both in Python and R. So it would be interesting to see if they, I don't think in the same notebook, you can switch between kernels. It's like it's their version of a kernel. Yeah. So as Oleg points out here, and he's pointed this out in the Discord as well, so people on Zoom can unmute themselves if they want to, because it's a birds of feather, so it's a open to the floor discussion.
Okay, I've got a question I'd like to ask. So we're using a Python package called Dask, which provides distributed arrays, but under the hood, these are represented as computational graphs. So it's quite nice to be able to, obviously it doesn't work perfectly all the time, but in the majority of cases, it's quite nice to dispatch a computational graph off to a scheduler, which then schedules work on multiple cores and nodes. But I mean, I've seen in Julia, there are packages like Dagger. I'd be interested in your opinion in how flexible, how flexible a graph one can create with a package like Dagger. And I think I've also seen there are distributed arrays in the main Julia library, but I think these, as far as I understand, those are backed by buffers. Or could you, yeah, I think what I'm showing is that I don't understand this very well, and could you clarify on these issues?
Yeah, I've not done, distributed computing, so I don't really have any experience with that. I was going to look into it in the future for the project that I'm working on right now, the software I'm developing. The author of Dagger told me to get in touch with him, so I think if you're interested in Dagger and what its capabilities are, I think, you should actually contact the developer of Dagger. I think he would provide, most of the stuff out there in Julia is, works pretty well. It's fairly complete, and it's, as I said, it's only getting better. The slide I have right now is what's kind of in the repository. A lot of this stuff is still kind of in its early stages. But what's in Julia Astro is really pertains only to astronomy. The rest of the Julia packages, there are lots of them that are much more complete. And so you're not just limited to what I'm showing on this slide is what I'm trying to say. The big issue is there's a time package, and what we've done is we've added aspects. The Astro time package takes what's there as a base and elaborates on it in terms of astronomy, and that's what a number of these packages do. Any other questions?
We also have a question here from Francisco. So for a working astronomer who is not a programmer and needs to do some analysis, say photometry on an image, is there a reason to learn Julia? What would they do? I don't know if you have any experience in photometry, so can you perhaps comment on that?
Yeah, it's difficult for me to comment on. I haven't done a photometry with Julia. There is a package being developed called photometry. There is actually a graduate student out at at the University of Hawaii who is using this for his exoplanet research, and so he's developing a lot of this code, and it's coming along pretty well. I mean, as an example, his transits package here, which I list here, is very competitive with the code that's out there in Python already. And he developed it. It only took him a couple of weeks to develop it. I think that's one of the big other benefits of Julia is you can actually get really high performance code up and running quickly. So I wish I could provide more, but I can't. I'm not that. Don't have that much experience with everything that's out there yet.
All right, thanks. Then Jonathan has also asked here, and you've briefly mentioned that you work with radio data through this as well. So he rightly comments that one big thing really in radio interferometry, I should say, is the data access layer. So we use Casa Core, or a large majority of the community, I should say, uses Casa Core either through the C++ layer or through the Python wrappers over it. So what's your experience like using, interacting with radio interferometric data?
Well, that I do have experience on. I'm writing a modeling visibility model, fitting program called VisFit, which I have a poster for. So that's where most of my experience with Julia comes from. VisFit, even though it's in its early stages, is very competitive with all the other visibility fitting programs that are out there. And my plan is to expand on it and make it much better. But it's currently, I use VLA data, and therefore I use CASA. So I have to read that's how I read the radio data. I use CASA core. It's a simple, as I go back before, I used the Python interface. Oh, where'd we go?
Your screen just dropped.
Yeah.
You can no longer see the slides.
Let's get back here. All right, there we go. And okay. Sorry for that delay. So if you go back to the interfaces, I do py quote import CASA core as something, and then I just use and then I import from once I've imported CASA cores, I import the tables interface or library, and then I just use the tables library to read the data out of the measurement set. I can do that within 2 or 3 lines of code. It accesses the underlying C++ code directly and loads it straight into Julia arrays. I can read several gigabytes of data within seconds. So, there's no delay, there's no anything like that. So in terms of, access to radio astronomy data, it's very fast.
Yeah, okay, that's good to know, because I know from our end, we've experienced that the Python global interpreter lock inside the Python wrappers for CASA core is actually a large bottleneck. So it's actually very interesting. I'm definitely going to try it out. All right, so let's see if there's further questions here. Michelle, you have posted a few more questions here. So she asks, do you have any examples of going the other way around? So calling compiled Julia code into Python. You can tell I have a very specific way of using Julia in mind.
Yeah, good question. No, I don't have any experience, doing that. I believe it is possible, though. But no, I don't have any experience doing that, so I can't elaborate on that anymore.
Okay. Of course, if you do that, you're going to run into the global interpreter lock again. So, you may get not so great cache performance, I would say, because only the bits that are written in Julia will be just-in-time compiled, right? And if you go back to Python, in the intermediate bits is going to be subject to the interpreter lock again.
Hi, can you hear me?
Yes.
Hi, sorry. So I'm Jonathan. I was asking some questions in chat. Thank you very much for your answer. I think it's very cool that you can use Python CASA, well, not Python CASA core, CASA core from inside Julia. One thing that's interesting to me then is how does that affect sort of package management and distribution? Because then you sort of, depending on how you're using it, you're going to end up with a lot of sort of complicated dependencies if you're including other languages.
Yeah. So, sorry, I'll get the answer out in a minute. So that was that's an issue that has hopefully been solved like a year ago. There is a Julia package called Binary Builder, and it was designed to basically build, static languages like C++ code, so that it can be, that you can use it in Julia. So, you have a Julia wrapper, but the underlying code is in C or C++ or Fortran or whatever. And this makes sure that the code is compiled correctly and everything links and works, transparently. My understanding is I've had no problems with, binary builder. I think people really like it. I think it, works very well. And so the way it works is that, every time you pretty much upgrade Julia or you upgrade your package, that code is rebuilt, okay? So you don't use an old version, you use the current version for, the version of Julia or the version of the package you're using. So yeah, there's that issue that you have lots of versions out there. But Julia Package Manager allows you to clean that up and, and maintain it fairly well. But there's usually very little issue where, you have this, version control issue where they're just not compatible. I've never experienced that, to be honest.
Thanks.
Things just work. I'm sorry?
No, thanks. That sounds great.
So Michelle just wants further comments. Yes, Micah.
Can you hear me?
Your mic's very soft.
Can you hear me now?
It's better, yes.
Okay. Hi. Thanks for running this. It's very cool. I've been pretty excited about Julia for quite a long time, but I think, as somebody who develops tools for the community to use, we are very entrenched in Python. But very often I have to do heavy computational tasks where I might do the same thing like 100,000 times or 1,000,000 times or whatever. So to compile that piece of code in the inner loop would be very valuable. And the attraction of Julia is that it's easy to write code that's then compiled and fast. So that's why I keep asking questions about how do you actually embed can you embed Julia into Python rather than the other way around? Because I think that's something that would be very cool, and that you could then the community would take that up much more quickly if there's bits of Julia kind of snuck into Python rather than the other way around. So I don't know if you have any experience with doing that, or if you have any suggestions of resources that I could play with, for example.
No, I don't have any experience with that, and right now I couldn't refer you to anyone. I'd have to ask somebody else who's who kind of works in that area. I'd have to ask the community. People will look a bit askance at why one would do that, but I'll try to get back to you on that.
Okay, cool. Thank you.
Any other questions from the floor?
Anything else? So while we're waiting, the last slide I have is what's next for Julia, and kind of part of the reason for the BoF was to find out if people are interested in Julia, what type of packages or software they'd like to see developed in the near term, the midterm, and the long term. Near term is the next few months, maybe next 6 months, and midterm is the next 12 to 18 months, and then long term is the next 3 years, 3+ years, something like that. The other aspect is, if we have a big enough community, then we should start thinking about working together and maybe creating a consortium to get people to move in the same direction. So those are just some ideas to think about. Express your opinion.
Simon, so you've posted here on Discord. I don't know if you want to unmute and ask a question in person, or
yeah, that's just a comment. I don't think it's really going to drive the discussion forward. But I think, I think what you're saying about a consortium I mean, to me, this starts. To me, that this means developing packages, which I think, like as you said, you started the process with Julia Astro. Sorry, I don't think my question's very formulated, so I'm just going to.
Well, consortium may not be the appropriate term if that's what you're saying, but the idea is to kind of get people working together and developing Julia, moving Julia forward, in a more parallel manner instead of ending up with lots of different packages.
I mean, are we like as astronomers, are we developing a language, or are we developing packages that use a language?
We're developing packages that use the language.
Yeah.
I mean, there's not much reason to, well, you can add features or look to try to develop features for the language, but the primary developers are highly qualified scientific computing people, so they have a vast knowledge of in terms of scientific computing. So trying to get new features added is probably would be difficult and require a lot of motivation. But there are a lot of packages that we can, and features we can provide. Astro Time is one of them. Is a good example.
Because I mean, I certainly was looking at Julia, and I mean, I personally made a decision to stick with Python and NumPy, and just because I think it seemed to me at the time that the package ecosystem in Python was more developed. I'm always expecting Julia to go from strength to strength. So I think at some point on the inflection curve, Julia is going to take over. I guess I'm hedging my bets here.
Yeah. No, it will take a long time. I fully understand it's going to take years,
Okay.
But, my thought is that if the community, the people who are interested in pushing Julia can develop really, a few state-of-the-art applications, which, are far superior to what's in scientific Python, then, that's where you get people, you start accreting users, because those are the tools to use. They're fast, they're robust, and that's how you get it. As an example, I'm hoping, my program VisFit becomes that, eventually for radio astronomy data. To be honest, I'm not happy with what's out there in terms of radio astronomy data, so I'm writing my own.
Yeah, I think as John mentioned earlier, I think it's the data access packages that I mean, that's the thing. Like the language as it stands is, as you pointed out, great for manipulating data and crunching it. I mean, I wouldn't sort of raise any serious criticisms against that. It's just like, yeah, radio astronomy data is usually associated with a CASA data table system, and we're gonna, to properly support that and everything that it implies, I guess to me seems a big task, and also to make it thread safe, because I feel that that's what CASA core's missing at the moment. Interestingly enough, there's a.
Well, I mean, Julia, I believe Julia is thread safe, to a large extent. I mean, that's a core aspect of it.
Yeah,
I don't mean to disparage SciPy. I developed it 25 years ago. I was one of the earlier developers on it, but I'm looking for something better. And just as an example, in analyzing, radio astronomy data, if you look at your monitor, in terms of CPU usage and so on, you're lucky to hit 20% CPU usage on, several cores while you're analyzing data. In my VizFit, I can run all 16 threads at 100% for 2 seconds, you know, and that's the way we should be doing computing. We're not using our CPUs effectively. Julia allows one to do that, you know, so that's what's amazed me is I can quickly use, you know, go full out on my you know, desktop. And other software just doesn't do that, even though it's written in C and C++ and Fortran. It was just bottlenecks in the design.
Yeah. So as I say, I'm not criticizing that aspect of Julia at all. What I'm saying is, like, in terms of access to the Casa table data system, what we have at the moment is either C++ or Python, and neither of them are inherently thread safe.
Right.
So
I've asked for documentation about, you know, the tables package, and there's no documentation. I couldn't, even if I wanted to write something in Julia, I can't because there's no documentation.
I actually,
that's not good software.
No. Yeah, but actually, there's I just want to point out, because actually, just to sort of confirm what you're saying, there's actually, I'll post it in chat. There's now a Python package being developed that tries to reverse engineer the wire format of the Casa data table system. So there might be the possibility to take all the sort of hard work that is being done by these people, you know, because they're just figuring out the wire protocol in reverse, you know, and then, you know, there'd be the possibility of taking that and, you know, writing it in Julia, and then you'd have like a full-on proper access layer for Casa core. So yeah, I take your point that the documentation isn't.
Let me take some other questions, okay?
Yeah, I'm taking up too much time. Someone else can go in.
So what else do we have out here? Anything else I should add? There's a question here. So Michelle has a comment. I haven't used it myself, but I've heard it's good, especially for differential things like ML. Are you talking machine learning and using Julia?
I think
That's
that was in reference to JAX here.
Okay. In Julia, there's a huge effort in machine learning, develop high performance code. In fact, I think they're talking about redoing Flux in Julia. There's a lot of discussion in terms of high performance computing and in rewriting a lot of the code that's out there, just because they can get much higher performance than, you know, what's available. But we'll see how that progresses. I know the toolkit is progressing, you know, quite quickly. That's out of MIT. People are using that for climate modeling. There's a big package called Klima, which uses it extensively. Any other questions or suggestions?
See any questions online?
I think we've lost a lot of our participants.
Is there any questions from our virtual participants here?
I guess less of a question and more just to sort of reiterate what was Michelle mentioned earlier, which is just that, you know, Julia is very appealing. There are lots of alternatives to Python out there that are very appealing. The issue really is the manpower hours that you have to invest to reach an equivalent point a lot of the time, given that there are also competing technologies inside Python, well, or Python packages which can potentially do similar things. So I think it's just worth perhaps talking about kind of, what are the things that we absolutely cannot have if we stay with Python? And I mean, obviously the GIL is the bane of our existence. We cannot get rid of it. There are projects trying to, but it's an incredibly difficult problem. But sort of just in general, what is Julia going to give us that we cannot have in any other way, I guess?
Yeah. I mean, that's a good question, good comment. And this is, it's the same comment or, issue whenever you come up with a new language. And, it's the reason people develop new languages is so that you can do more with less code. The code is more expressive, the language is more expressive. The reason we went with Python and, and NumPy was because it was more expressive than C and Fortran, and, you had to get people on board and with that. Julia is, it's the same issue with Julia is having, why should I change? I have all of this code out here. But if you can get the same performance and the same capability in a third the code or, with Julia, than you can with, scientific Python, then it takes, then writing that code or re-implementing the code only takes a third amount of time, okay? So you can actually get more done. And if the code runs faster, then you can get more done. So what I'm trying to say is most people feel that, it took me 12 months to write this application. I'm not going to spend another 12 months to re-implement it. But, if it only takes 2 months to re-implement it, maybe you might want to think about it, particularly if you're going to get much higher performance, in the long term. So that's the trade-off. And that's the argument, that's kind of the big argument for, for staying with SciPy and moving over to Julia. My experience with VizFit is there's a Julia package out there, or I mean, not a Julia, Casa package out there written in Python and C++, okay? It started using NumPy, but the NumPy arrays weren't fast enough. So the core computations are done in C++. That's a lot of code. That's several thousand lines of code, all right? My application is comparable to that, to UV multi-fit, which is a nice little application. But I only have, mine's written in 500 lines of code or less. And to add new features only takes a few more lines. I mean, it's more of a design issue for me to understand how exactly I want to design it and how I want the interface to work. But the number of lines of code are not a lot of code, and that's the point. And therefore, code is time. Lines of code is time. So.
Good.
Thanks. I think that's a great point. One thing that I think might aid in convincing people is sort of, if you actually have comparisons, or someone's done the comparisons between something like Julia and the various JIT compilers for Python, because I take it with a bit of a grain of salt whenever people talk about performance, because it really is just a question of how you've implemented it and what you use to implement it. Like, it is completely plausible to get something like NumPy or Numba or any of those things, absolutely blasting away on all threads on a CPU. It's just a question of, is the problem correctly set up? So I think it's always nice to back up these comparisons with numbers.
But that you pointed out the macro at threads. I mean, the macro at threads only took me a second or two to type in, and now I have full threading on my system. If I was to do that in SciPy, that would take me days to understand how to set that whole procedure up. Okay.
I mean, I
In
guess
Julia, it doesn't take me any time at all. So that's what I'm saying, you know.
No, I absolutely hear you. But I guess the point perhaps I'm making is that I don't actually think SciPy is what you should be comparing against, because I don't think SciPy is offering the same thing. SciPy is a whole bunch of bundled, predefined code. Julia, you'd be writing these things yourself. So then you need to start comparing against things like Google JAX and Numba and all of those things, because you know it's right. A lower level thing, really.
Sure. Well, here maybe I don't know if this is an appropriate response or example, but everybody uses FFTW, right?
Yeah, I mean,
fastest Fourier transform in the West, right?
It is an option for Fourier transforms, yeah.
Yeah, so. Well, it's, you know, Stefan Karpinski, you know, who's one of the creators of, you know, Julia, believes it's the fastest implementation out there. So, but he's now thinking of rewriting it in Julia, but re-implementing the whole thing in Julia, because he thinks he can get better performance than in the C++ in the code he's got right now. So, and you know, there's talk of re-implementing BLAS and LAPACK, you know, in Julia, because they think they can get better performance than the Fortran. So, you know, if people are considering this, then there must be something to it. So, but
yeah, I mean, absolutely.
I don't really, you know, I don't want to, you know, I don't want to stay on this issue of, you know, arguing Julia. You know, I'm a convert. I'm just trying to explain out there, you know, let people know what Julia can do, and you know, have them take a look at it, see if they can help them, you know, do their research.
No, I mean, I think that's a very noble ambition, and I think Julia is really interesting.
Okay, we have a question here from Peter as well. So he asks, so several questions. Let's start with the first one. Does Julia replace the need of using something like MPI for clusters? What's your thoughts on this?
Gee, you know, I haven't really used MPI all that much. So I really can't answer that question. I think it was brought up earlier that there is a package called Dagger designed for distributed computing. And, but I have not had a chance to use that yet. In terms of how does it perform on different architectures, that really is dependent a lot on, you know, the LLVM compiler and what it understands about the architecture that it's running on. You can speed things up. I mean, the compiler will, you know, takes the most conservative look when you provide it code. If you can provide it, you know, additional information and say, oh, you know, this loop, you know, you can use the @SIMD, you can vectorize this loop and give it that expression, then you can get factors of, you know, 1,000 improvement, you know, just by doing that. You know, what I'm saying with Julia is you can, you know, sometimes it helps to help the compiler in terms of optimization. And usually that help is, you know, just adding in a macro, preceding an expression with a macro and or that type of stuff, or providing, you know, the proper the data type for various, you know, for the variables. Does that answer your question?
Well, Peter hasn't responded yet, but
yep.
Yeah, he said yes. Yes. All right. Michelle just comments on that. Yeah. So as we said, Python is a pretty terrible out of the box example of dealing with parallel calculations. So if you add something that could be trivially parallelized, then there's not quite an easy solution in Python to do that. I've known that from my personal experience as well. That's quite the case. So yeah, so at least so there's to some degree and architecture agnostic as well. So this could be probably the biggest selling point of Julia, if it's a lot easier to parallelize stuff. Yeah, and then she just added a comment here. Someone should rewrite OpenCV in Julia.
Well, to go back to, the why Julia, there's the issue of parallel computations. As I said, there are macros, and there are several different macros. One is SIMD, which is basically telling the compiler you should vectorize this loop. And I had someone a couple of weeks ago who's learning Julia write a simple loop. I forget exactly what he was doing. And he said it took, several seconds to run over 1 million elements. And then he added the @SIMD in front of it. And it took less than a millisecond. He was like, what the hell? Why is this? And it's like, well, you gave the compiler a little more information and it was able to really optimize the code effectively. And as I've said with, my experience with for loops, I've used @threads to, use all the threads all at once on my processor. I can use 16 threads and I use all of them. And that sped up my calculations by a factor of 16. And then there's the other option. You can write code for your GPU using @CUDA. You write it in Julia, and the code is compiled to NVIDIA GPU. You can also use AMD GPUs with a separate package, and you can do parallel computation that way. The kernels don't have to be big. They can be, just a few lines, a function that's a few lines long, but, you can take advantage of the GPU that way. And I'm still experimenting, with how best to get the performance out of the system. With my radio data, I need good high performance. So I hope that helps.
Definitely, I think that's, yeah. She says taking advantage of the GPU would be be very cool. Yeah. I think I'm speaking on the correction here, but I'm not sure how good the support for this in Numba is, but the LLVM compiler in that also has support for GPU-based operations. But if it's already built into a language that's Julia, I think it's probably a much better option. Especially in the radio regime where we have huge arrays, and if you can trivially write a parallel operation on that, it's actually well worth considering. So,
yeah. So, to go back to the radio data, and this goes back to my experience, with my own program, VisFit. If I want to fit, a source to the radio data or several sources, I can typically just write a single line function in Julia, which, will be compiled to machine code to do the optimization. That's my function to be optimized. In Python, you have to write a parser, you have to write kind of your own language to take that function and compile it down, so it's interpreted by machine code to get high efficiency out of it. Julia pretty much gets rid of that whole step. So, all code runs at, machine speed. And that's another example of, why it takes less code to develop in Julia, because the environment allows it, the language allows it.
I think John here just commented on this. So the GPU in Numba does exist, although it's non-trivial. So that could easily point in Julia's favor.
Yeah. I know Numba, is competitive and, does similar things to what Julia does. But as I said before, I think for a lot of people, Numba will be fine for what they need to do in terms of computations. But I just kind of get the impression that there are certain limitations, to it. And it's just because of the Python language, So, I mean, I loved Python 20 years ago. So don't get me wrong.
Paul, it strikes me when you talk about the performance that one can obtain with Julia. I mean, because I've looked for these kind of like these performance benefits, obviously in Numba and also in Google's XLA compiler land. So that's Google JAX. And I think generally what we find is that you either have to write for loops or you have to depend on those kind of compilers' ability to create what are called fused kernels, where they take a bunch of related operations and then put them all together or generate the optimal code that one would get from writing for loops. And it strikes me that Julia is probably doing the same thing under the hood, though they might not call it that. Do you think that's correct, or am I?
Oh yeah, Julia will.
Yeah.
Julia will look at your for loop, and if it, kind of an aspect, part of, in parallel or with a compiler, what's the right word? It will unroll that. It'll unroll that, wrap that loop. It'll unroll that loop to get higher performance out of it, and you don't really have to worry about that.
But what I'm interested in is if you give it, if you construct a computation out of arrays. So if you do array programming, will it in turn sort of decompose the memory access pattern into something very optimal that uses the registers in the right place, as one would do with writing for loops? That's what I'm interested in.
Well, in basic SciPy or NumPy, when you add or multiply a series of arrays together, it's a binary op. The array array A times array B is multiplied together. A temporary storage is being created. Then you add it to C. Okay.
Yeah.
SciPy gets rid of that, and it will just take every element, if you're doing element-wise, addition, and unroll that. Okay. It will essentially vectorize that entire expression, so there are no temporaries anymore. Okay, so if you're doing A times B plus C, well, CPUs have a pipeline for that, right? So it takes advantage of that pipeline of addition, plus multiplication plus addition, where SciPy can't take advantage of that because it's doing binary ops.
Yeah,
does that explain?
Yeah, I think it's just it's interesting to clarify those to clarify those points, because if Julia can do those kind of thing, that's where
Julia does that all the time.
R is coming from. Yeah, thanks for clarifying that.
Anything else?
Anything from the floor?
If not,
Anything from the floor? Nothing from the floor.
okay.
I've got questions.
Well, no more interest. I want to thank everybody for participating and showing interest. And feel free to contact me if you need any additional information. I do appreciate the link to the cost of formats IO link. That's much appreciated. I'll take a look into that.
Yeah, thank you so much, Paul. So yeah, I know from my side, I'm definitely keen on trying this out in my next set of commissioning scripts that I'm going to write. It's definitely, if I can parallelize things easily, then it would be really cool. So thank you so much for your presentation here.
Yeah, thanks for your help and assistance. I appreciate it.
All right, so Peter says here, thanks so much for the intro. Please prepare.
Okay, I will consider a tutorial.
Yeah, definitely. Awesome. All right, thanks so much for our online participants who have joined and the in-person participants here. Thank you so much for joining and for the great discussion we had on this.
Yeah, thanks, Paul.
Yeah,
Thanks,
thank
Ben,
you
for
very much.
hosting.
Thanks.
Cheers. Bye.